Review, Unit 7, Alkyl halide substitutions. We're going to talk about the mechanisms of SN1 and SN2, a decision tree, how to decide whether your conditions are telling you to do SN1 or SN2, how to draw products with the appropriate stereochemistry, and one last type of problem. I'll give you a product and you have to tell me what alkyl halide and nucleophile you would use to get that product. This is actually more like the second review. The first review is a previous video, 07G20, where we did go over steps to decide whether a reaction is going to be SN1 or SN2. Remember, it's going to require you looking at the type of alkyl halide, primary, secondary, or tertiary, the type of nucleophile, and even possibly the solvent. But I'm going to give you some really good clean-cut rules on how to decide that. Okay, so again, this is review 07G30, and let me show you. I already forgot what I'm supposed to talk about. Mechanisms? Yeah, we'll do mechanisms, and then we'll do the decision tree. Okay. The easier of the two is SN2, because if you look at look at the cat cartoon, I never gave credit. The credit goes to this website, Master Organic Chemistry, which is actually pretty good. I refer to it a lot. And the one that takes the least number of steps is actually this bottom one, because the orange cat comes in, the gray cat leaves at the same time, and you're done. Whereas SN1, which is the top row, the orange cat has to wait until the gray cat is compelled to leave. They form a carbocation, and then the orange cat moves in. So there are multiple steps to do an SN1, whereas SN2 almost always has just one step. Okay, but let me show you that real quick, and we'll do SN2 first. We've done this many times, the mechanism, but each time I'm going to try to give you a new nucleophile so you get used to all the different nucleophiles that can be used in a substitution reaction. That's why this is not really a good unit to do a roadmap. It's not as if we have a molecule that could have 8 different reactions. We have a molecule that could do substitution, but it can seem like a lot of reactions because the nucleophile can change, but if you could interpret the nucleophile correctly, it's the same reaction, right? So it's not like you have a lot of reactions. You only have one reaction. Well, technically 2, SN1 and SN2, and those could change a lot just based on the nucleophile. So again, it's not really a good unit to do roadmap. It's more that you have a list. Okay, you just collect every nucleophile that you see in your practice and just jot it down. And maybe you could even categorize it as a poor or a good nucleophile. There are easy ways to do that as well, and I think we'll have time to do that. So SN2. SN2, because the orange cat wants to jump in right away, most likely your alpha carbon, the carbon next to the halide, is going to be uncrowded, very easy to access. Okay, so I'm purposefully making this primary. Now, that orange cat is pretty aggressive, so we're going to make a good nucleophile, or we're going to use a good nucleophile. And a good nucleophile could be... I'm not going to use that. Oh, how about this? This is a good nucleophile. CH3SNA. Huh? Why do I think that's a good nucleophile? Anything that's anionic, for the most part, is going to be a good attacker because it has a negative charge and wants to neutralize it, right? So we're going to realize that when you have a group 1 metal, that's sodium plus, and technically it's a salt, but the salt will dissociate in your reaction, and give you these two species. There's your nucleophile. It's negative. So anions are typically very good nucleophiles. Okay. I'm not going to draw the mechanism right now. Let me draw the final product. The final product is this. See, think of it. The S is the attacker, so the S has to be the one attached to the dot. The S brings along with it a methyl group, and you could use line structure to show that's the methyl group. The S is neutral. S is like oxygen, neutral when it has two bonds and two lone pairs. Okay, so when it's filling the product, just draw that. Okay, when it's mechanism, you got to show the lone pairs. So the mechanism, SN2. Again, this is the short mechanism because the orange cat is pretty aggressive. It's a good nucleophile. It's an anion. Okay, that's a 3. I'm not showing any solvent. I could show solvent. Okay. You would want to use a polar aprotic solvent. Okay. These are all tips. These are all notes that were talked about in the previous videos. I'll use a green pen for the mechanism. Orange cat kicks out the gray cat at the same time, and we have this. Okay. There are other things you should know about SN2, and these were discussed in the previous video. One of those is the stereochemistry. You usually get inversion, but we don't see inversion here because, see, this carbon is not chiral. Okay, so don't draw any dashes and wedges in this case. Alright? You know that is bimolecular. That's what the 2 stands for. That you have 2 molecules that are required to go through the rate determined step. Okay. The purpose of this first page of notes, though, is to compare and contrast SN2 and SN1. Why do you think, okay, we're doing SN1 now, why do you think the cat is waiting? Okay? Why do you think the cat is waiting for the leaving group to leave? Well, one possibility is that it's very crowded, tertiary. Alright, so think about that. Or you should think about tertiary is crowded. If it's crowded, the nucleophile has to wait. That means SN1. It has to wait till the gray cat leaves to make more room for the orange cat to come in. So this represents the forming of the carbocation. Oh shit. I just realized cation, cat. Anyway. Man, how could I use that? Anyway, SN1 always goes through a carbocation. Alright? And normally, if you want to make an SN1 reaction, or make it go through SN1, you want to use a crowded alkyl halide. By making it crowded, what are 2 things we accomplish? By making it crowded, we're able to make a very stable carbocation, but also by making it crowded, we kind of prevent any nucleophile from coming in right away. Now the nucleophile I want to use here is, I'll use even a weak nucleophile. Okay. Heck, you know what? You know how I can make this weak? By protonating it. See, that will not dissociate like it does up here with the metal. There's no metal here, so we don't have an ionic bond. Okay. And usually we add a little heat. Okay, because it's kind of sluggish. We have a bad nucleophile. We have a crowded alkyl halide. We gotta add a little heat to make it go. And when we make it go, again, your sulfur is your attacker. And you could draw a line, or you could write CH3. I'll draw a line. But the thing you want to remember is with these neutral nucleophiles, you gotta remove the hydrogen at the very end, because if we didn't, that sulfur will be positive, and that's pretty acidic. It wants to be neutral. It doesn't want to have a charge usually. Okay, neutral molecules, for the most part, are more stable than their charged counterparts. Okay. All right, time for mechanism. The cat the gray cat leaves on its own. Okay. And that's our first step. And I always say that the step where the gray cat leaves is always the slow step. And it is, in real life, the slow step. So on the screen up here, top, the slow step, actually you need 2 molecules. Here the slow step you only need 1. Okay, that's why it's unimolecular. That's what the 1 stands for. Yes, we did create a Br minus, but we're not going to use it. Okay, just like I'm sorry, like over here, we did create a Br minus. I'm trying to keep consistent. If I'm going to expect my students to draw all the products for each specific step, or for the preceding step, I'm going to have to do that myself. Okay. Even though I'm not going to use it, right, in the next step. In the next step, what am I going to use? I'm going to use this. And I'm drawing it backwards so the sulfur is a little bit closer. And good. Then we have this. I'll write CH3. And then, yeah, we could use a Br minus. Okay, be a little bit neater than I am, for the sake of your grader. And okay, that should be the product. Okay, you don't have to draw the lone pairs. Okay. Rate determined step, unimolecular. Okay. Now, what if I had chosen tertiary and I gave you a good nucleophile? What if I gave you an orange cat that was aggressive? So we have to make some decisions, because you know the crowded nucleophile tells me SN1, tertiary is SN1, but the good nucleophile typically tells me SN2. I'll tell you now that the type of alkyl halide is usually the winner, the decider. So you're going to like this. At least my class is going to like this. I'm going to give you some steadfast rules. Okay? Methyl halide. Oh, by the way, I have to put a disclaimer here. Methyl rules for substitution. Okay. There's also competing elimination reactions, but a lot of times, maybe not a lot of times, but some professors will try to keep those separate. You have substitution, you have elimination, and they don't want you to decide whether you have either or even both. So when I give you these rules, these rules only apply to substitution. Only apply to substitution. The rules, as you know, in total. Okay. You wouldn't apply these to elimination. All right. So methyl halides, like this, CH3Br. Do you see how that's very uncrowded? Your decision is always SN1. Did you hear my mistake? Always SN2. It's very uncrowded. It's very easy for a nucleophile to come in and kick out the leaving group. It's always SN2, always, regardless of whether you have a poor nucleophile or a good nucleophile. Okay. Yeah, I wish I had. Let me write this a little bit better. Always SN2, regardless of the nucleophile. Primary alkyl halides. You know, here's a primary. Do you see the difference? Actually, I don't mention methyl halides very much, but that's not primary. There's actually no carbons attached to that carbon, so that is just simply a methyl halide. It's even less crowded than a primary. A primary would have to have another carbon attached to the dot. Always SN2. Sure, I know what some of you are thinking. Well, what if I have a solvent that favors SN1? What if I have a poor nucleophile which usually favors SN1? It don't matter. You know why? Because primary carbocations are very unstable. I can't think of a situation where you would ever draw a primary carbocation. So if a carbocation is impossible for this primary alkyl halide, you cannot do SN1. SN1 has to go through a carbocation. Always SN2. Okay? Secondary. On the fence. Now, yes. Let the nucleophile decide. Okay? For instance, or for example, if you had this, okay, that's a good nucleophile, but what if we have a neutral solvent? Let the nucleophile decide. Let the nucleophile decide. Now, if you have two reagents, you're going to assume that the neutral one is the solvent. Okay? This is an assumption, but this is a good assumption. Because in practice, you don't dissolve anything in a liquid anion. That's always something that you add to the liquid solvent. Okay, so this is a nucleophile. Let the nucleophile decide. In this case, SN2. Now, if you had only water, then water is the nucleophile and the solvent. And yeah, if water is the nucleophile, then it's SN1. SN1. Okay, so do you like this table so far? Because tertiary, we're back. We're back to always. Always SN1. Always SN1. Okay, so that's great, because really, it's automatic. If it's methyl, primary or tertiary, you know what to do, because you have the always. Secondary, you'll have to make a decision, but let the nucleophile decide. Okay. I think we have a couple of examples. Yes. Let me just make sure before we go to those examples if I'm missing anything. Yeah, why not? Let's go to the examples. Go ahead and pause your video and copy problem number 1. Okay. So here's the first problem, and then there are 2 more. If you want to copy them and pause the video, it's those 2. Very interesting. We have a Newman projection. I don't think many of us were expecting that. Okay, in the substitution problem, but it's a halide, alkyl halide. All right. Let's read the directions together. Draw the substitution products. So it could be plural. Use wedge dash drawings when appropriate. So we are worried about stereochemistry. If you're worried about stereochemistry, remember SN2 occurs with inversion because of backside attack. SN1, you form a carbocation. Carbocations are flat, and the nucleophile can come in from either side 50-50. In these circles, you're going to state whether the mechanism is SN1 or SN2. Oops, secondary. So we're going to let the nucleophile decide. But this molecule here, there's only one reagent, so this is both the nucleophile and the solvent. And when this acts as a nucleophile, it is neutral. So that's a poor nucleophile. And also it's a protic or a polar protic solvent. Both of those tell me that it's SN1. The fact that it's polar protic and the fact that it is a poor nucleophile. Before we forget, why don't we just fill that into the circle right now, SN1. Okay, make sure your 1s don't look like 2s, like mine almost did. Ah, oh, my goodness. Is that 1? That's a 1. With SN1, you go through a carbocation. So the bromine leaves on its own. Imagine a carbocation that looks like that, with a plus charge right there. Carbocations are sp2 hybridized. They are flat. So that nucleophile could come on the front, or it could come from the back, which is underneath the paper. Remember, also, with your neutral nucleophiles, you got to get rid of that hydrogen. You got to get rid of that hydrogen. We literally did it in the mechanism. Okay? It's typically the last step. It's always the last step, actually. Okay? I'm going to draw the first one, wedge, O, 2 carbons. I'm not going to do the condense. I'm going to take the shortcut. And because that molecule can come from the front or the back 50-50, 50% of the time, 50% of the time, our other enantiomer is this. So, yes, you do form what's called a racemic mixture. It doesn't say here to state racemic, but I'll just do it anyway. These are different molecules. They're actually mirror images of each other if you flip this one. Or flip this one, it doesn't matter. They are, you could make these models and show that they are mirror images of each other. Here's the one that we don't have to panic, okay? Don't have to panic. Now sure, we could draw out the line structure, but when we draw out the line structure, we would have to figure out if this is R or S, because what this is telling me is that we have a very good nucleophile, cyanide, and we have a polar protic, polar aprotic, which in the previous video I explained why it favors SN2, and good nucleophiles favor SN2. SN2, that's a 2. And yeah, try to do the correct formatting. Capital S, capital N, subscript, normal 2. This dude right here, with its lone pair, it's the best way to attack this carbon, right, to kick out the chlorine, is from what's called the backside. Okay, so literally, I am drawing it from the behind this chlorine, and this chlorine pops off. Okay. The challenge is, how does this change the Newman projection? You could draw it a couple ways. Let me draw the back carbon exactly the way it looks, though, because nothing happened to the back carbon. There's a couple ways to do this. Literally, the CN is right here. Right? That's where the CN came from. And because we want to make that Y shape, right, the 120 degrees, it looks 120 degrees, right? We all know that this is 109 because it's tetrahedral. But that CN now is in between this H and this methyl. So if you draw the Y, in this case the upside down Y, like this, I know it looks eclipse. It doesn't matter whether you draw the eclipse or staggered. What matters is that the CN is in between the H and the CH3, but in this order, H, CH3. You can't switch those two, right? So imagine that this bullet comes in, heck, let's call this umbrella and a gust of wind. The gust of wind comes in and it inverts the umbrella, and these two snap this way. Bam. That's what we get. Now, if you really want to draw the more stable conformation, just rotate the front carbon and maybe put the CN group on top. But when you do that, do you know where the H and methyl group go? They have to go H here, methyl group here. If you do the reverse, you did not do backside attack. Okay? That's why it does make a difference. stereochemistry. When your carbon, right, when your carbon is chiral, and this carbon is definitely chiral because it has 4 different things on it. Okay. Make a model. You'll see that the ease of attack is from the backside. There's a lot of space here. It can't come from the front. You're going to bang right into the chlorine. Okay. All right. This is easy. From our rules, primary, always SN2. What's hard is, what is our nucleophile? We have a sodium. So we know that that sodium is positive, which meant that that carbon is definitely negative. That's your nucleophile. Put a dot. Please put a dot. Because that dot has to be connected to this attacker. And that's where you put the triple bond. Now you can draw it horizontal. Okay? But I like to show that the triple bond is linear, which means that the 4 atoms around the triple bond are all in the same plane. Count carbons. That's another cool trick. 4 carbons. 1, 2, 3, 4, 5. 4 plus 5 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Many times, people are going to lose this bond here and put the triple bond right on the dot. That's not true. The triple bond is not at the dot. The triple bond is between these 2 carbons. Okay? Okay, I know I went through that fast. You could always rewind and go through it a little bit slower, but I do want to get to these types of problems because these are substitution products. This N3 was a nucleophile, and we made this bond here. So the molecule that was the alkyl halide looks like this. Now, look what I'm going to do. I'm a little afraid of this bond. Why? Because my nucleophile was nitrile, which is the same as what? N. Okay, now I'm going fast. You could pause it. Did I say nitrile? I meant azide. Azide. That tells me good nucleophile, negative, SN2, inversion, backside attack. Do you see why I'm doing this? Dash, because I have wedge as a product. That azide does backside attack, meaning it attacks from the opposite side of a dash. So the opposite of dash is wedge. So that bond is important to determine whether it's wedge or dash. This is the only answer. Or you could just simply write this, N3 minus. That's perfectly fine. If you want to, give me the anion without the counter ion, that's perfectly good. Okay? That's your prerogative. Right? But for me, I usually put the salt. See this pink dotted line? Super important. See, it's my atom that's not a carbon that's usually doing the attacking, right? The nitrogen, the oxygen. The other thing you can do is put a dot. That dot's super important because that's the dot that was attacked. Okay, so in this case, I am going to just use the anion. Okay. Those 2. What can you do? Ask your classmate, what product do I get if I give you this reaction? Hopefully they draw this one. If they don't, someone's wrong. Either you gave them the wrong starter material, or they gave you the wrong product. Ask your classmate this. What would you draw as a product if I gave you this? Okay, there's your dot. There's your good nucleophile. It's an anion. It's secondary. Let the nucleophile decide. SN2, come in. It doesn't matter SN1 or SN2 because this carbon is not chiral anyway. So it really didn't matter. Alright? Alright, good luck. Try to do some textbook problems if you can. But this is a really good problem to to demonstrate that you really understand SN1 and SN2.